Hi, this lesson is about functions. So a function is a rule that assigns for every element x exactly one element that we call y. And remember that y and f of x mean the same thing, but f of x is called functional notation. So when you see f parentheses x, that's not f times x, it's read as f of x because f is a function of x. In other words, y is a function of x. So two examples are here on the right. The first one, y equals x squared, is a function, and the second one, y squared equals x, is not a function. So although they look similar, there are differences. So let me explain why. So y equals x squared is a function. So for every value x, there is only one y value. So here are some examples. When x is 1, y is 1. When x is 2, y is 4. Because all you have to do is square the number that x is, and you get your y value. And x really could be any number. I just picked 1 and 2 as an example, but x could be 0 and y is 0. X could be -1 and y is 1, but you only get one answer for y. In contrast, y squared equals x. Well, in most cases, this will give you two answers for y, with the exception of 0. So when x is 0, y is 0. But for example, when x is 4, y is plus or minus 2. And that's because when you have an equation like this, I let x equal 4, the way you solve for it is that you take the square root of both sides. And when you do, you have to remember that there's a positive and a negative answer. So 4 and plus or minus 2 for y is one example of where this function, of where this rule is not a function. It's actually called a relation. But there's many other examples, like when x is 1, y would be plus or minus 1. And again, the only exception is 0, because when x is 0, y is 0. So let's practice using functional notation. Here we want to evaluate f of -1, given that f of x is negative x squared over 2x squared plus 1. This type of function is called a rational function because it's a fraction, where you have a variable in the numerator and the denominator. So you have to plug in -1 everywhere there's an x. So that's exactly what you see here on this line. So I have negative, and then in parentheses, -1 squared, because you do have to square the -1 before you take the opposite sign. And then the same thing in the denominator. You have to square the -1 and then multiply it by 2. So when you do that, -1 squared is 1, but then the opposite sign of it makes the numerator -1, and my denominator becomes 2 plus 1. So your answer is, or your function value is -1/3. So when x is -1, your y value is -1/3. This next example is a little bit more abstract because we're taking a function of another variable that I'm going to call a. So we're going to evaluate f of a, and then we're going to do that again for f of a plus h. So not only do I have more than one variable, I have an a and an h, but I'm also adding those two. Okay, so the concept is the same. To evaluate f of a, we're going to have to plug in a in our function, which I gave you a quadratic this time. So that's exactly what you see here. You get 2a squared minus 3a plus 1. And there's really nothing else you can do with that because these are not like terms. So that's your final answer for f of a. Now, when I substitute a plus h, like this asks you to do, that means everywhere there's an x in your f of x, you have to replace it with a plus h. And whatever is being done to x must be done to a plus h. So that's exactly what you see here. I have 2 times a plus h squared minus 3 times a plus h. And make sure you put the parentheses around the a plus h because this is -3 times x, and your x is now a plus h, so it has to be -3 times a plus h. And then the plus 1. The plus 1 doesn't change because the 1 doesn't have a variable. And then the rest of the work is just some algebra. You have to expand and combine like terms. So the first thing I did was I FOILed this, And so the answer is below. I'll do it here on the side, so just to remind you of how to FOIL. So FOIL stands for first, outer, inner, last. So your first terms are the ones at the beginning of each binomial, so that's a squared. Outer are the two on the outside, so that would be the a and the h. So that's plus AH. I would be the inside terms, so the ones closest to each other, so that's the H and the A. And H times A is the same as A times H. And then your last term are the two terms at the end of the binomial, so that's the H and the H at the end of the other one. So I get H times H, which is H squared. But these two are like terms. So I get a squared plus 2ah plus h squared, which is exactly what you see here. So that's the expanded or the FOILed a plus h. And then the rest I just wrote down. But now in the next line, so this one here, I'm going to distribute the 2 and I'm going to distribute the negative 3. So I get 2a squared plus 4ah plus 2h squared minus 3a minus 3h plus 1. And none of those are like terms, so there's really nothing else you can do at that point. Okay, so we'll be using functional notation in this next topic, which is the difference quotient. So by definition, the difference quotient of a function f of x is f of x plus h minus f of x over h. So that's a really important definition later on for calculus. So we introduce a form of it now so that you can practice your functional notation and get used to plugging in an x plus h, simplifying, and so forth. So your numerator will be different depending on what your function is, but your denominator should always be h. Okay, so let's practice in these next couple of examples. So we start with a quadratic function. I have negative 3x squared plus 5. So remember, the numerator has to be f of x plus h minus f of x. So let's do the f of x plus h part first. So that's exactly what you see here. The x gets replaced with x plus h, and everything else should be the same. So the negative 3 should be in front of the x plus h. We have to square the x plus h, and then the plus 5 doesn't change again because it doesn't have a variable. The second part of the definition is that we are subtracting f of x. Remember, f of x is what's given, so it's just minus that function. And make sure you put it in parentheses because the minus belongs to the whole function, so we're going to have to distribute that negative at some point. Okay, so in the next line, all I did was I FOILed this, so just like I mentioned before, first, outer, inner, last, so that's what you see here. Remember, your denominator is just h, just as I mentioned before, that's by definition. So when I FOIL x plus h, you'll see this line here, negative 3 times negative 3 times, in parentheses, x squared plus 2xh plus h squared, and then plus 5, and then minus negative 3x squared plus 5 all over h. And then in this line, I distributed this negative 3, and then I distributed this negative. So we see negative 3x squared minus 6xh minus 3h squared plus 5 plus 3x squared, and then minus 5. So now, and again, all over h. Don't forget that denominator. So from this line to the next, all I did was combine like terms. So several or a couple of them cancel. So the negative 3x squared and the positive 3x squared cancel. And the positive 5 and the negative 5 cancel. So you're left with negative 6xh minus 3h squared all over h. Now again, this is a rational function. Rational functions must always be left in simplest form. So the way to do that is to factor out an h from the numerator, which is what you see here. So I have h times negative 6x minus 3h all over h, and then the h's cancel each other out, and your final answer for the difference quotient is what you see in the box, negative 6x minus 3h. Okay, so let's practice another example with the difference quotient. This time I gave you a rational function. So I have g of x equals 2x over x minus 3. And I'm also using g instead of f. So your difference quotient definition is still the same. I'm just going to write it in terms of g instead of f. So it's g of x plus h minus g of x all over h. Okay, so let's apply that to g of x. So here's your difference quotient. The x's change to x plus h. That's the g of x plus h part of it, and it has to change in both the numerator and the denominator. And then minus g of x, well, that's just minus your function, so that's exactly what you see here. And then the whole thing is over h. Now here, the algebra that we have to do is a little different than what we did in the last one because it is a rational function. So I need to simplify my numerator, and my numerator are these two rational functions. So that means I need to identify the LCD. The LCD is the product of the two denominators, so it's x plus h minus 3 times x minus 3. So I need to rewrite that numerator with a common denominator. So the first rational function is missing the x minus 3 in my LCD. So then I multiply numerator and denominator by x minus 3. The second rational function, which is this one, is missing the x plus h minus 3. So you have to multiply numerator and denominator by that x plus h minus 3, both in the numerator and the denominator. Okay, so in the next line, I actually show you that I'm going to be multiplying those. I also distributed the 2 here. So I get 2x plus 2h times x minus 3, and there's my common denominator. And in the second rational function, you're going to have to distribute the negative 2x across the x plus h minus 3. And again, there's my common denominator. Another thing I did on this line was instead of writing divided by h like this with the big fraction bar and the h in the denominator, I decided to write it like this because it's easier to explain what I do in the next line. So I want you to see what happens to the h. So in the next line, I am foiling these two and distributing the negative 2x. So that's what you see here. I have 2x squared, that's first. Outer is minus 6x, inner is 2xh, and last is minus 6h. And then distributing negative 2x gives me negative 2x squared minus 2xh plus 6x. And then dividing by h is the same as multiplying by the reciprocal of h. All right, so you learned that back in pre-algebra. That's how you handle fractions. So that's times 1 over h. And so now I have it all written as one single rational function because they have a common denominator. Okay, so now I have some like terms in my numerator. So I can cancel quite a bit. So the 2x squareds cancel, the 6x's cancel, the 2xh's cancel, and I'm left with just negative 6h over x plus h minus 3 times x minus 3 times 1 over h. But that allows us to cancel the h's. The negative 6h becomes just negative 6, and the 1 over h cancels. So your final answer, your difference quotient, is negative 6 over x plus h minus 3 times x minus 3. All right, so that requires some practice on how to use difference quotient. So here's a little bit more about functions. We're going to look at this from a different perspective. Functions can be defined from verbal expressions. So suppose I want to express the rule as a function. So, and here's the rule: cube, then subtract x. And so this notation is telling you that your input is x. So I have to cube x and then subtract 5 from it. So f of x is x cubed minus 5. Here's another example. Express this as a function of h. So this should be an h here. So, and again, my input is x. It says add 1, then square it. So that means add 1 to x and then square that result. So h of x is x plus 1 in parentheses to the second power. Okay, so here's more with words. Suppose the perimeter of a square is defined by the formula P equals 4S. Define S as a function of P. So in this case, S is the independent variable. P is the dependent variable. So S being the side of the square, the perimeter being dependent on what that side is. So if we turn the tables and define S in terms of P, that just means that you have to divide 4 on both sides. And so S is equal to P over 4. And once you define it in that way, you would consider P to be the independent variable and S to be dependent on P. So it's just a matter of manipulating the original function. Okay. So here's more vocabulary. We have something called the domain and range. The domain of a function is the set of all possible values of the independent variable. And remember, we usually call that x. And the range of the function is the set of all possible values of the dependent variable, which we usually call y. But you don't have to. They don't have to be called x and y. That's just common. And so when you're determining domain and range, you're only considering real numbers, not imaginary numbers. So anything that would result in an imaginary result for y, that would be excluded from the domain. And also any values of x that would result in dividing by 0 would also be excluded from the domain because division by 0 is undefined. So that's where the tricky part comes about. Domain and range is keeping in mind these restrictions. The most basic of all of your functions is the linear function. And so we know that a linear function is a function where the highest exponent of the independent variable, which is again usually x, is 1. So y equals x is a linear function because this is x to the first power. But so is something like this, negative 2x plus 5. That's also considered linear because the x is only raised to the first power. But this is not a linear function. That's actually a quadratic function. And this one's also not a linear function because although the x is to the first power, it's actually in the denominator. So if I were to write it in a different way, this is to the negative 1. So you can't have x in a denominator and consider it a linear function. And we'll talk about all these other functions, quadratics and rationals and whatnot later in the course. So the graph of a linear function is a straight line. And in order to graph a line, you need at least 2 points that satisfy the equation of the line. So there are 2 general ways to state the function of a line. So the first way is consider standard form. This is where your x and your y are on the same side. So ax plus by equals c, where a, b, and c are numbers, are real numbers. And the other way, which is the more convenient way to work with lines, is y equals mx plus b, where m, the coefficient of x, is the slope, and b gives you the point 0b as a y-intercept. So slope and y-intercept are useful information to have in order to graph a line easily and also to understand the behavior of the line. So the domain and the range of a linear function of this form, y equals mx plus b, is always all real numbers. So there are exceptions to lines, like vertical lines and horizontal lines don't have all real numbers as their domain and range. But when it's in this form where you have a slope and a y-intercept, and it's the graph is either going up from left to right or it's going down from left to right, those will have domains and ranges that are all real numbers. Okay, so we want to graph y equals negative 2x plus 1. So here your y-intercept, we get it from here. That's 0, 1, and we have a slope of negative 2. So you can graph this in one of 2 ways. So one way would be to plot 0, 1 first, and then this slope would mean that you would go down 2 units and right 1 unit, and that's what I did. I went down 2 units. So I went down 1 unit to 0, another one to -1, and then 1 to the right, and that gave me the point 1, -1. Another way to plot, get a secondary point for a line is to insert any value you want here for x, multiply it by -2, add 1, and that would also give you another point on the graph. So here's another one, y equals 3x minus 2. Here your y-intercept is 0, -2, and again that comes from here. Your slope is 3. So if I'm applying the same technique, 3 is the same as 3 over 1. So first plot 0, -2, then go up 3 units and right 1 unit. So if I go up 3 units from 0, -2, I end up at +1 for y, and then 1 over to the right, I get my secondary point, which is 1, 1. You can also plug 1 in here and get 1 as a result for y, or plug any number you want in for x, like -1 or 2, and still get a second point that will give you the same exact line. So in both cases, both the first example and the second example, my domain and my range are all real numbers. This is how you express it in interval notation, and this is how you express it in set builder notation. So with set builder notation, this might be new for you. This R that looks like it's got 2 lines in front, this means the set of all real numbers. Okay, so that's how you state it in set builder notation. Okay, so let's graph another line, but in a specific way. We're going to identify the x and y intercepts of this line, -3x plus 2y equals -6, and then sketch the graph. All right, so first let's find the x-intercept. The x-intercept is when y is 0, so that's the work you see here. So when I plug in 0 in for y, I get -3x equals -6. Divided by -3, you get that x is 2. So the coordinate of the x-intercept is 2, 0, because remember y was 0. To find the y-intercept, you do the opposite. You let x equal 0 and then solve for y. So that's the work you see here. Plug in 0 for x, solve for y, you get that y is -3. So remember, x was 0, y is -3, so that's your y-intercept. So the x-intercept is where the graph intersects the x-axis. The y-intercept is where it intersects the y-axis. So that's exactly what you see here. Here's my x-intercept, here's my y-intercept. Connect the 2 points, and you have your line. And again, because this is a linear function, your domain and your range are stated here. This time I did it in both interval notation from -infinity to infinity, and also in set builder notation using R to represent real numbers. Okay, so this is D for domain, R for range. This fancy R means all real numbers. Okay, so here are 2 exceptions. Here, horizontal and vertical lines. So this time I want to graph this line, y equals -1. So when your function is in the form y equal to a number, you're going to get a horizontal line. So here's my grid. Here's my x and y plotted in this dark pink color. To plot -1, that means you go down 1 unit and you sketch a line horizontally from left to right. So this time my domain is still all real numbers, because x could be anything, but your y is a single value. Your y will never be anything other than -1. So the way you express that is you put the -1 within the curly bracket. So it's just the set of -1 is your range. In contrast, here I have x equal to 3. X equal to 3 is a vertical line. And in order to plot that, you see I have my x and y axes in green. I've gone over 3 units and sketched this vertical line in purple. So I have a line going up and down. So this time it doesn't even make sense to talk about domain and range because this is not a function, because for every value of x, I have infinitely many y's. So I gave you one example here, 3, 0, but 3, let's say this is 2, 3, 2 is also on here, and also 1, 2, 3, let's say 3, negative 3 is also on here. So x is always 3, but your y is any number on this graph. And remember, when we first started this lesson, a function exists if for every x there is one value. Here I have one x that maps to infinitely many y values, so it's not a function. Okay, here we have quadratic functions. Quadratic functions are of this form. That's your standard form where you have your ax squared plus bx plus c. Your terms are all separated by pluses or minuses, and the highest exponent is 2. So it's a second degree polynomial that makes it a quadratic function. So the domain of a quadratic function will always be all real numbers, but your range is going to be restricted. Remember, range are the y values, and that depends on what the vertex is. So parabolas, all parabolas have a vertex, and the formula for the vertex is that you find your x value by computing negative b over 2a, and then you plug in that value into your function to get your y. And the b and a values come from the original function. It comes from here. A is the coefficient of x squared. B is the coefficient of x. Okay, so let's work with this. Let's sketch a graph of a quadratic function. The graph is going to be called a parabola. And then identify the domain and range for this function, and we're going to use both set builder and interval notation. So f of x equals x squared minus 4. So notice that it looks a little different than what I said here. That one has 3 terms, but x squared minus 4 only has 2. That's okay. As long as you have an x squared as your highest degree, this would be considered quadratic. Okay, so let's identify our a, our b, and our c. So a is the coefficient of x squared, so that's 1. B, which is the coefficient of x, well, that doesn't exist, so it's 0. And c is the constant, so that's negative 4. So your vertex, remember, it's this formula, negative b over 2a. So I get negative 0 over 2 times 1. So my x value is 0. Plug in that value into your function, and so f of 0 gives me a value of negative 4. So your vertex is the point 0, negative 4. And remember, that's either going to be the lowest value or the highest value on the graph, and that depends on the direction that your quadratic function is pointing in. When a is positive, your parabola will be facing upward, so it's be an upward U. But if a is negative, it's going to be an upside down U. So here's our sketch. I got a couple of other points here. These are called x-intercepts, and we'll talk about those more in later lessons. But so here's our graph. Here's my vertex, 0, negative 4, and it's an upward facing U. So my domain is all real numbers. X could be any value, a positive, a negative, 0, fractions, decimals, could be anything. So again, you express it like this. This is a set builder here, and here's interval notation. But your range, well, it really helps to see the graph. Your range are all possible values of y. And here's your y-axis. So if I look at my y-axis from smallest to largest, meaning from the bottom to the top, the first value that y obtains or results in this function is negative 4. And then it will take on all values greater than or equal to negative 4, because these arrows mean that this graph goes on and on forever. So the way you express that is that you would say that y is the set of all y such that y is greater than or equal to negative 4, or in interval notation, it is from negative 4 to infinity. because remember, this arrow means your numbers are going towards infinity. So here I showed you the work on how to find the x-intercepts. You find x-intercepts by letting y equal 0. So you get, I use square root method to solve it. So you get x squared equals 4, so x is plus or minus 2, which are these two values that I plotted here. Okay, so we're going to sketch another parabola. So this one is more traditional in that all of the terms are there. And then we're going to also identify domain and range. So here, this time your a is -1 because that's the coefficient of x squared. Your b is 3, that's the coefficient of x, and your c is -2. So remember, your vertex formula is -b over 2a. So when you simplify it, your x coordinate for your vertex is 3/2. Then you take your x value and you plug it into your function. So you're going to get -3/2 squared plus 3 times 3/2 minus 2. So we're plugging it into this. So when you square the 3/2 and take the opposite sign, you get -9/4. Here, when you multiply these two, you get 9/2, then minus 2. So you can see that you're going to need a common denominator. So the common denominator for 4, 2, and 1 will be 4. So this gets multiplied by 2, and this one gets multiplied by 4 in the numerator and the denominator. So you get -9/4 plus 18/4 minus 8/4. So when you simplify that, you get 1/4. So your vertex is 3/2, 1/4, which is the same as 1.5 and 0.25. So it helps to see it either as a mixed number or as a decimal so that you know where to graph it later on. Okay, so again, I'm going to find x-intercepts just to give me a little bit more information. So we set it equal to 0. I'm going to factor out a negative first so that my x squared is positive. So I get x squared minus 3x plus 2. And then the factors that work are x minus 2 and x minus 1. So you can ignore this. This is just a coefficient. So you solve both of your factors. You get that x is 2 and x is 1. So we have x-intercepts at 2, 0, and at 1, 0. Okay, so that's exactly what I plotted here. Here's my vertex. Here's my x-intercepts. And the graph is an upside down parabola because my a value, or my leading coefficient, is negative. So we saw that at the very beginning. Your a is a negative, so it's upside down. So here, just like I mentioned at the beginning of this topic of quadratics, your domain is all real numbers. This is set builder notation. The second one is interval notation. You should know the difference between the two. And your range, again, if I'm looking at this from the bottom to the top, these arrows here mean that this is going towards negative infinity, and then it's increasing, and the biggest y value that it takes on is 0.25 or a quarter. So your set builder is, the range is the set of all y such that y is less than or equal to a quarter, or in interval notation, it goes from negative infinity to 1/4. So make sure your intervals are always written from smallest to largest. Okay, so now let's talk about domain of a rational function. Remember, a rational function is a fraction, and you must identify the real number values of the independent variable that will result in division by 0. When you do, those will be your exclusions to the domain because division by 0 is undefined. So not all rational functions have exclusions, but oftentimes they do. So we want to state the domain in interval notation for the following function. So here, this is a rational function. I only have one variable in the denominator, but it's still considered rational. So you take your denominator, set it equal to 0, and you get that x is -3. That is not a solution. That's an exclusion to the domain. It's a restriction. So your domain in interval notation is the set of all x except for -3. So that goes from negative infinity to -3, and then from -3 to infinity. So remember, these always have to be written from smallest to largest, and we want to show that we are skipping -3. So here's another one. This one's a little bit more complex, but it's still a rational function. You take your denominator, set it equal to 0. This factors into x minus 8, x plus 6. So again, you get two solutions here, 8 and -6, but they're not solutions, they are restrictions. So let me show you a better visual to figure this out. So -6 and 8 were the answers we got. -6 and 8 have to be excluded from the domain, but everything that I am shading in is in the domain. So that means you're going to have 3 intervals, and you write them from smallest to largest. So the first interval goes from -infinity to -6, then from -6 to 8, which is this middle part, and then from 8 to infinity. And we put union symbols between them. The U means union, which it means and. So those 3 intervals give you the domain of that function. All right, so here's another one. I have 7t over t squared minus 9. Again, take the denominator, set it equal to 0. Again, I use the square root method. I get 2 answers, plus or minus -3. So again, if a number line helps you to visualize it, put your 2 answers on here, -3 and 3. Those 2 are excluded from the domain, but everything else that I'm shading in is in the domain. So it goes from -infinity to -3, then from -3 to 3, and then union 3 to infinity. So here's your domain. So here's one more. I have u squared over u squared plus 3. Again, take the denominator, set it equal to 0. This time I get an imaginary number solution. I get that u is plus or minus I root 3. That is not a real number. So that means there is no value of u that would result in division by 0 that is a real number. So therefore, there are no restrictions to the domain. Your domain is all real numbers. So there are exceptions, but oftentimes you do have restrictions or exclusions from the domain. So let's move on. This time we're talking about the domain of a square root function. You must exclude values of the independent variable that result in an imaginary number result. And remember, how do you get an imaginary number? That's when you take the square root of a negative number. And we'll only be talking about square roots here, not higher roots. So just to remind you, the square root of -4 is 2i. The square root of -7 is I root 7. So we're going to state the domain in step builder notation of the following. So I have here the square root of x minus 3. So the first thing you want to do is figure out where is it equal to 0. It is all right to take the square root of 0. Square root of 0 is just 0. You just can't have 0 in a denominator. X minus 3 equals 0 when 3 is 0. So 3 is part of the domain because 3 minus 3 is 0 and the square root of 0 is 0. So that's why I put this number line here and I put a solid point on the 3 because I want to include 3 in the domain. But now I have to test. You have to test a value less than 3 and then a value greater than 3. And it could be any number. So suppose I pick a number less than 3. Suppose I let x equal 1, because you could pick anything you want less than 3. If I were to plug in 1 minus 3, that would give me a -2. That is not a real number, so anything less than 3 is not in the domain. But if I plug in a number greater than 3, like let's say 4, let's let x equal 4, then 4 minus 3 is the square root of 1, which is a real number. So you want to include the 3 in everything that I'm shading, everywhere that gives me a positive result on the inside. So the way you express that in interval notation is that your domain is a set of all x such that x is greater than or equal to 3, because you want all values from 3 and greater than 3. So here's another one below. I have h of t equal to the square root of t squared minus 4. Again, first start by letting the inside equal 0 to get those solutions. And so you get plus or minus 2. So that means that negative 2 and 2 are part of your domain, because when you plug those in, you'll get square root of 0. But then you have to take test points. So pick something less than negative 2, like negative 3. Plug it in here. That gives you a positive result. So if you plug in negative 3, for example, you'll get 9 minus 4. That's the square root of 5. That's positive. That's a real number. If you pick a number between negative 2 and 2, like 0, and plug that in, you'll get a negative result. That's square root of negative 4 is imaginary. It's negative. So we know that negatives within a square root are not acceptable. And then if I pick something greater than 2, I also get a positive result. So everywhere that I have a positive result, I want to include it in the domain as well as negative 2 and 2. So in set builder notation, it's the set of all t such that t is less than or equal to negative 2. That's the left side of the number line. Or t is greater than or equal to 2. So that total is your domain. Okay, here's one where we're combining both radicals and rationals. I have a radical in the denominator of this expression. So it's a fraction, but I have a radical in the denominator. So just like my last two examples, I'm going to take the inside part of the radical and set it equal to 0. So when you solve that, you get that x is equal to negative 4. So that means if x is negative 4, I am going to have the square root of 0 in the denominator. That is not okay, because dividing by 0 is undefined. So this time when I put my number line to keep myself organized, I'm going to put an open circle at negative 4, because I do not want to include it. And then you pick your test values. Pick a number less than negative 4 and plug it in here. So if I pick something like negative 5, I'm going to get a negative inside of the radical. We know that's imaginary. That also has to be excluded from the domain. But if you pick something greater than negative 4, like negative 3 or 0 or 2, it doesn't matter what you pick, and plug it in here, I get a positive number inside the radical. Positive number inside the radical gives me a real number result. So everything that I'm shading has to be in the domain. So here your domain is the set of all x such that x is greater than negative 4, but not including negative 4. All right, so now we're going to consider domain and range in terms of these graphs. So I've given you 3 graphs here. So here, my domain, it looks like my x values start at 0, and then it moves to the right forever and ever. So your domain is from 0 to infinity, including 0, and the way I know that is because I have a solid point at the origin. But your range is different. You read your range along the y-axis. So this looks like it's implying that it's going to keep going down. So here, your range goes from negative infinity and ends again at the origin at 0. So make sure you always state your intervals from smallest to largest. So you read the x-axis for your domain, you read the y-axis for your range. Okay, number 2, this looks like a quadratic function. Remember, if I'm reading my x-axis for domain, then it looks like I'm going to take on every single x value throughout. There are no breaks. This graph, this parabola looks like it's opening forever and ever. That's what a parabola does. It just keeps getting wider and wider. So you have no restrictions on domain when you're dealing with a quadratic. But your range, if I look at this from bottom to top, the first y value that it takes on is negative 3, and then it grows from there. So your range is from negative 3 to infinity with a square bracket around the negative 3. And then finally, this last example here, number 3, it looks like I have this graph that's connected all throughout, but here I have a hole. This open circle is called a hole, and that's at the point 1, 2. So that means 1 is not in the domain, and 2 is not in the range, because that's where it is undefined. So the way you show that is that your domain is from negative infinity to 1, union from 1 to infinity. So in other words, skip the 1. But your range is from negative infinity to 2, union from 2 to infinity. So for the range, you need to skip the number 2. All right, so what's a piecewise function? Piecewise function is a function that is defined by different rules depending on different values of the domain. So you have a function that's defined in 2 different ways. I have f of x is x plus 2, which is a line when x is less than 0. But it's defined as negative 2x, which is a different line when x is greater than 0. So in order to graph a piecewise function, you have to graph each part, the x plus 2 part and the negative 2x part, but you have to pay attention to what values of x you can choose. So here's the work for x plus 2. It's this chart right here. So even though it says for values less than 0, you still want to know what it would be at 0, and then pick one number less than 0, like negative 1. So I picked 0 and negative 1, I plugged it into x plus 2, and I get 2 and 1. So I have a point at 0, 2, and another one at negative 1, 1. So that's exactly what you see here. This is the line on the left. 0, 2 has an open circle because it's less than 0, not equal to 0. And then here's the point, negative 1, 1. And then you connect that open circle and that solid point to the left, and there's your line x equal to 2. I do the same thing with negative 2x. Again, you want to know what it would be at 0. So at 0, it would be 0. And then pick one number greater than 0. It could be any number, like 1, 2, 3. Plug it into negative 2x. So I picked 1, and I get 1, negative 2. So here's the 1, negative 2. Here's the 0, 0. Connect those 2 points to the right because it's defined greater than 0. And there is your piecewise function. All right, so identifying domain and range is a little bit trickier with these. With domain, you really can look here. This is telling you that you have some definition for all values less than 0, another definition for all values greater than 0, but it's never defined at 0. Like there's nothing that says x equal to 0 or less than or equal or greater than or equal. So therefore, you have to skip 0 in the domain. So your domain is from negative infinity to 0, and then from 0 to infinity. To determine range, you really need to read this graph. So these 2 lines are telling you that they're going towards negative infinity. So it's definitely starting at negative infinity, and then the biggest value it will take on is 2, although not quite equal at 2 because it's open. So you write this as the interval from negative infinity to 2 with a parentheses around 2 because it's not equal to 2. All right, here's another piecewise function. I have h of x is equal to x squared or x minus 3, and that depends on the interval. So it's equal to x squared for values of x less than or equal to 0, and it's equal to x minus 3 for values of x greater than or equal to 1. So here are my points for x squared. This is a parabola, but we're only going to be able to show half of it. So I pick 0 and then a value less than 0, like negative 1. So I get 0, 0, and negative 1, 1. So those are these 2 points here. So this is the graph of x squared. And then we need to graph x minus 3. That's a line. We start at 1 because it's greater than or equal to 1, and then pick another number greater than 1, like 2 or 3. I picked 3. So we get these points, 1, negative 2, and 3, 0. So here's the 1, -2, here's the 3, 0. You connect the 2 points going to the right only because it's greater than or equal to 1. And so there is the graph of your piecewise function. So you always graph a piecewise function on the same grid because this is one single function defined two different ways. So your domain, you can get that from here. It's defined for all values of x from -infinity to 0, that's this part, and then for all values from 1 to infinity. But between 0 and 1, nothing is defined. So we skip that, and you also don't see anything here, right? That's between 0 and 1. There's nothing that corresponds on this graph. And then your range, you read from bottom to top. The first value that y attains is -2, and then from there it grows forever. So your range is from -2 to infinity. Okay. So a polynomial function is a function that has terms with exponents that are whole numbers. So we talked about some of these already. This is considered to be a linear function because it's x to the first power. This is a quadratic function because it's x to the second power. And then you can have higher order polynomials. Here's an example of a fourth degree polynomial because the highest exponent is 4. So with polynomial functions, you should have no exponents that are fractions. You should have no radicals. You shouldn't have any variables in the denominator. So examples of functions that are not polynomial functions is this one. This is your radical function. This one, which is a rational function. So the nice thing about polynomial functions, so anything like this, is that your domain is always all real numbers. You don't need to look for restrictions or exclusions. So here's some vocabulary regarding polynomials. This is a polynomial with 4 terms. The variable terms are the first 3 with all the x's. The constant is the one that doesn't have a variable. We call -3 the leading coefficient because it is the coefficient of the variable part that determines the degree, and the degree is 5. So the highest exponent in a polynomial function is the degree. And like I mentioned, the domain of a polynomial function is always all real numbers. So here's net change. The net change in the value of a function f is as the input changes from x sub 1 to x sub 2, where x sub 1 is smaller than x sub 2, then the net change is f of x sub 2. In other words, plug in the bigger one first, minus f of x sub 1. So it's basically the difference in your y values. So if f of x equals -2x squared, as x changes from -1 to 3, your net change is f of 3 minus f of -1. So you just plug in 3 into -2x cubed. So you get -2 times 27 minus, and then -2 times -1. So you get -54 minus 2, which gives me a net change of -56. Another example is here. The net change of this rational g of t is equal to 3 over t squared as t changes from 2 to 4. So that means that you subtract g of 4 minus g of 2. Remember, always plug in the bigger one first. Otherwise, you're going to have the wrong sign. So g of 4 is 3 over 4 squared minus 3 over 2 squared. That's 3/16 minus 3/4. We need a common denominator of 16, so this one gets multiplied by 4 in the numerator and the denominator. So you get 3/16 minus 12/16, which gives me an answer of -9/16. And that can't be simplified, so that's it. Okay, so there's quite a bit in this section. Please work through the homework carefully. Good luck.